Hello, my name is Saisubramaniam Gopalakrishnan. I am a research engineer at the Institute for Infocomm Research in A-STAR, Singapore, and along with my co-authors Pranshu, Haytham, Savitha and ArulMurugan, we present to you our work on knowledge capture and replay for continual learning. First, we'll see the motivation and the key contributions of this work, and we'll also show what we mean by flashcards and the proposed approach. We'll use flashcards for knowledge capture and subsequently for replay in continual learning. As a general modification, we know that neural networks learn to extract task-specific information from the given training data, and they store them in this network parameters or weights. What we're interested in is to extract and utilize this encoded knowledge representation, especially when data is no longer available in the future. So we know that transfer learning and knowledge distillation are good for single tasks, but we are looking at a unified and a consolidated representation that evolves with their growing data characteristics. Key contributions, we propose a new approach that can capture these consolidated learned knowledge representations onto visual images, as what we term as flashcards. Our work is the first to focus on continual reconstruction and denoising across heterogeneous image tasks. In task-incremental classification, we show that flashcard is task agnostic, is better than generative replay, and is also on par with episodic replay without additional memory overhead. So first, let's focus on training an autoencoder by feeding in samples from xn up to x1 up to xn, sampled from a distribution p of x belonging to dataset dt. We use the conventional mean absolute error to optimize for theta. After training this autoencoder, we are going to define epsilon1 and epsilon2 as lower and upper bound of when we are going to pass the training data again and get the difference between the reconstruction and the original image. To capture knowledge, we are going to make use of p of m, which is a different but well-defined distribution in the same dimension space of p of x. But these samples are completely different from the original training data. The output of the autoencoder for when we pass an mi is given by equation 3. So we're going to do our recursive passes or iterations of mi through the trained autoencoder such that we obtain this output FRI. And we're going to have another set of lower and upper bounds gamma 1 and gamma 2, which are going to define the minimum maximum error between the two successive iterations. Now, if we have two properties such that gamma 2 is less than epsilon 1 and that the latent space distribution of ft, which is the flashcard construction set extending to the original data dt, then by our hypothesis, we claim that these can be used as alternatives to the original data. So as an illustration, we can see that these random patterns are having a latent space projection which is different from the original data. As we keep on iterating at a particular point between 10 and 20, these two property 1 and property 2 are satisfied, and these can be taken as flashcards. Subsequently, due to the irreducible error in the autoencoder, noise propagates, and with the incoming iterations, we can see that the P2 is no longer satisfied, so that we cannot use those anymore. And this is explained with algorithm 1. And in algorithm 2, which is for replay and continual learning, we are going to make use of algorithm 1 to get the consolidated learned knowledge up to task tt. With the new data, with the dt plus 1, we are going to train for theta t plus 1 by passing these flashcards as an additional loss constraint, as a replay constraint. First, we are going to see how flashcards can be used as an alternative to the original dataset by taking ImageNet reconstruction as an example. So when we train an autoencoder on ImageNet original data, the reconstruction error is around 0.10. Now, considering we replace this with flashcard construction, we can see that the performance steadily improves from 0.17 up to 0.13 when we go for 1 million flashcards. The second use case is on knowledge distillation. When we train a teacher network AE1, we are going to get a corresponding reconstruction error. When we construct flashcard from this teacher and then train two student networks AE2, smaller and larger architecture, the performance is as comparable as when we train the original data. So next we go for continual learning as a replay mechanism. We do not look at homogeneous tasks because we find that reconstruction is trivial and does not induce forgetting, as seen here. Instead, we focus on heterogeneous reconstruction and denoising by a sequence of 5 different datasets, and also for continual classification with sequence of 3. So for continual reconstruction, we're going to compare with two baselines. One is regularization methods and the second is replay. We find that as compared to generative replay, flashcard performance is 40% and 21% better than generative replay. And for as against regularization, we have 9x and 6x improvement for reconstruction and denoising. Visually also, we can see that without any continual learning, there's complete forgetting. Continual VAE based design introduces artifacts, whereas our method is better. Finally, on task incremental learning, there are two cases. One is with task ID and without task ID on inference time. Without task ID, our method is stable, is more robust. We can see that there's no dip in performance, whereas other baselines are having a sharp drop. Takeaways: we can use flashcards for consolidated knowledge capture, and they can be used as an alternative to the original data. And also, when used as pseudo replay, they outperform regularization and generative replay mechanisms. And we would like to thank I2R for code funding and also create program for the supporting this work.